Hi, everyone, and thank you for joining us for part one of our two-part virtual calibration webinar series. My name is Dana Pellegrini, and I will be hosting today's webinar. In the next 30 minutes, we'll share how virtual calibration offers a solution to significantly cut development time while also greatly lowering calibration costs, which will ultimately result in better products being released faster. I'll start by introducing today's presenter, Michael Bambola. Michael will then discuss common calibration challenges and how virtual calibration addresses those challenges, saves money, and shortens development time by combining simulation with physical tests. We will then close with a live Q&A. If you have any questions at any time during the presentation, please type them into the Q&A panel on the right-hand side of your screen, and he'll answer as many questions as he can at the end of the presentation. At this time, I'd like to introduce our presenter, Michael. Michael is a senior engineer and has been with Gamma for almost a year. Prior to joining Gamma, he worked at Cummins for almost 4 years, where he used GT Suite for developing models for use in virtual calibration on active program developments. Without further delay, I'll move it over to Michael.
Thank you, Dana. So a little bit about what we're going to talk about today is the process of calibrating a powertrain today the way it is. A little bit about what is virtual calibration, some of the common challenges that you may face during calibration, how virtual calibration can save money, and how it can help you meet compliance regulatory requirements. So today's process, from what we understand from our customers, is usually it starts at a performance group where the performance group tries to identify the operating space and sort of develop a base calibration around that. Then it moves to an emissions group where they focus on the emission system, and because in today's environment, the most important thing is emissions output. Then a diagnostic team will work to tune the diagnostics for the regulatory requirements and just diagnostic requirements for the engine reliability. The next group would be an altitude or off-nominal calibration group, which would then calibrate the engine for operating ambient conditions that are not typical, like sea level. They would take it high altitude. And then the final group would be a transient or drivability calibration group, and that would be a lot of time-intensive testing as well as potentially vehicle testing. And then all of those teams look forward to the test trips, to the diagnostic demo days. And so those are basically event-driven days. They happen potentially once a year. And based off of those trips, they will reiterate their calibration. And then they will iterate back and forth between the groups, leveraging whatever aspect of the calibration has a deficiency. And basically, that is a very time-intensive process. We have heard that the iteration could be a third of the entire time of the calibration program. And there's a lot of questions that come up, basically, is from performance, they would ask, did we get the most performance when we did our calibration? Emissions team would wonder, is the emission system robust? Diagnostic team would wonder if they've tuned the diagnostic too loose or too hard, so is it going to be too sensitive or not sensitive enough? The altitude or basically off-nominal calibration team will wonder, is the system going to react as they expect? And the drivability team will wonder if the operator perceives any issues under transient, like stumbling or anything like that. So in order to talk about the benefits of virtual calibration, we first need to go over what is virtual calibration. So what we have seen many customers doing is they're at the software controls verification with map-based plant model phase. So they're taking map data from test cell, putting it in a controls environment, and just exercising the model, seeing will EGR position change when given this input, and if it changes positively, if it opens, then that's okay. If it goes the other way, then there's an issue. That's literally just a verification. The next phase would be base calibration development, and that's what we see a little bit less of groups doing. and that's developing calibration for your engine using a full control system. Or you could do it with open loop by using just big DOE maps. You could understand the operating space. And then the next one, which we see almost nobody doing, is virtual test trip. That one would be replicating your summer test trip or your winter test trip or your altitude test trip, and you would need full controls buy-in for that. The final one, which is the most advanced area of virtual calibration, would be control strategy development with the physics plant model in it, which would be our GT power model, and doing robust control studies. So you're varying all of your actuator inputs and sensor outputs across a bell curve or so, or you're making the components in the powertrain model degrade, and you're determining what your controls will do when exposed to that. So a lot of these virtual calibration tasks that I've defined need basically 2 or 3 groups to participate in. And every OEM has these already. They have a simulation group that develops the models. They have a calibration group that calibrates the powertrain. And they'll have a controls group that develops the controls and is in charge of the software releases. For open loop, you would really just need 2 groups to talk to each other, which would be the simulation group and the calibration group. Traditionally, we see that they're a bit more separated, but with more integration, they'll be able to deliver a lot of value through the virtual calibration. And then for closed loop virtual calibration, which would enable you to do all of these, you would need collaboration between controls group as well. So those are 3 separate groups that we see in a lot of our customers, that if they work together, they would be able to achieve this virtual calibration process. Now that I've talked about what is virtual calibration, I'm going to explain a little bit about the value of virtual calibration. So the value of this virtual calibration is trying to reduce the iterative testing component that occurs during calibration. It's definitely not trying to replace the test, but what it is doing is it's basically able to reduce a third of the cost of calibration. A third of the calibration program is basically iteration, and it'll reduce a third of that. So that's like 11% of your entire calibration program cost. That's what we've seen customers project. And as you can see on the slide, we're not saying that it's going to replace the test. Testing and test trips are inevitable. You would never want to not do a winter test trip, but you wouldn't want to be out on the winter test trip troubleshooting your diagnostic or control strategy or testing different calibration releases on the trip. Some of the challenges that I'll go over that we see from calibration teams is damage during the test. So from a performance team, one of the riskiest tests to do is peak torque curve exploration. So you're trying to just reshape the torque curve maybe for a new program or even a special customer who wants more torque on their engine, and you'll develop a custom calibration for them. What we've seen is that when damage occurs, the test is stopped. If it's in a prototype phase very early, there's also a very large cost component to stopping that test. People who are calibration engineers hearing this might say that many test cells have checks in place to shut down the test when the engine is going to be potentially damaged. But I personally have seen that that's not always the case. And another thing is the engine could be inadvertently aged. So we see that sometimes with motorsport customers. They're unable to perform tests for very long because the engine will be aged so much that it becomes almost pointless to continue with that aged engine. So basically, it's for this phase, you could do it in open loop. You can understand your operating space and then proceed with the actual test to finalize the calibration content. For the test trip, there's a lot of challenges. Many customers go to Alaska and that's, you can see from the map, it's a very long trip. They're very critical events, and they cost a lot of money. They're in very high demand, as some of you listening may know. There's numerous meetings that are held prior to the test trip to get justification to fit your diagnostic in on the trip or your calibration in on the trip to test, because that's taking time away from another business critical team. But you want to make the most of the trip. You don't want to be out there troubleshooting. And then another risk that we see is potentially that the trip is missed altogether due to scheduling, or even you project, 3-6 months in advance that you're going to have cold temperature. You get there and it's actually not as cold as you expected. And then that would be a wasted trip. And those are out of your control as a company, but you could still proceed to do the virtual test trip with a virtual calibration. You can set the model to operate in an ambient condition. You can test how your powertrain performs with when it's exposed to a colder ambient. So you're able to still develop calibration content based off of that. Robustness is another challenge that we've seen. Calibration engineers usually struggle with performing a robust calibration because that requires you to take into account degradation, sensor variation, drive cycle variation, or part-to-part variability. Trying to account for either one of those is going to take a lot of time and effort and money. An example would be the part-to-part variability. That would require you to either machine the part to be degrading, or you're pulling parts off the line and evaluating, do these fit within the bell curve, where in the bell curve are they, and then putting it back on the engine, rerunning that, and seeing how that engine will react. So this is another challenge that we see. As you can see in here, also for some of the heavy-duty customers, there's a plot from California Air Resources Board where they want the emission system to be warranted for roughly 80% of the life of the vehicle. And that is a huge challenge because you don't know how your emissions will drift throughout the life of the vehicle. It's a very difficult thing to answer. And with virtual calibration, you could study that effect and create a robust control solution if your controls is able to compensate for the degradation. So how does virtual calibration help? Really, the key is that it's parallelization of the calibration process. What we see is that most programs will have maybe 6 test cells, maybe a dozen if you're lucky. And those test cells inevitably have to be run sequentially per test. A calibration engineer who has virtual calibration would be able to run a dozen test cells or more all at the same time in parallel and use that to get a result in virtual in the same time it takes for one test to be finished in the physical world. And also you would be able to have one engineer test their calibration on a virtual trip all around the United States. They would be able to run a test trip in Alaska, Death Valley, Florida, all at the same time, and be able to actually develop through that and basically have the test trip devoted to their calibration in virtual. And virtual calibration can also help for compliance and regulatory requirements. Basically, for diagnostic tuning, many engineers are trying to determine the threshold when the controls strategy is set. They have a threshold that they're able to vary and basically determine when the check engine light would come on. It's tied to emissions output usually, but some diagnostics are purely based on reliability, and you would want the powertrain to maintain a safe operating range when it's running and the diagnostic turns on. A lot of these questions of what level should the threshold be tuned to, and is the algorithm suitable, or is it robust to drive cycles? These questions, you'd be lucky to get an answer to one of them because they're very expensive. But if you get the answer wrong, or you're unable to answer it and it becomes a problem, then we've seen large warranty penalties be incurred on our customers, as well as, there's a potential for a brand and image perception that could impact our customers. But through virtual calibration, you'd be able to potentially answer that question better. So, in conclusion, for virtual calibration, a lot of automotive organizations already have pieces of this. They have the simulation model from the simulation group. They have the controls system from the controls team, and they have powertrain calibration engineers. Really, virtual calibration requires putting that all together and incorporating it into the current calibration process can save a significant amount of time and money. There's no more really waiting on the test cell, waiting in line, worrying about engine damage or failure or degradation during the test. And if anyone is interested in pursuing a virtual calibration type workflow, please reach out to us. We're more than willing to help with that. And this is something that we've helped before with other customers, and if you're really interested, we're definitely willing to help. And now I'll bring it back to Dana.
All right, thanks, Michael. We'll start the Q&A in a minute, but first there are a few things that I'd like to mention. If you'd like to learn more about the content presented today, please contact us. Like Michael said, we'd be happy to discuss your specific calibration challenges and help you to find a solution. Michael also wrote a series of blogs that go into more detail on the benefits of virtual calibration, with blogs that focus on a virtual calibration overview and then the specifics of open and closed loop virtual calibration. He also wrote about the benefits of OBD, so if you would like to learn more about any of these topics, I encourage you to check out our blog. As I mentioned earlier, this webinar is the first in a two-part series. Our next webinar is on March 31st, and it will explain how to implement virtual calibration into your development process. We'll be covering topics like balancing fidelity, predictiveness, and computation speed, steps taken in an effective workflow, and co-simulation environments for mill and sill. So if this sounds interesting to you, or if you know anyone who would find it helpful, please visit our website to register or share the link with your colleagues. You may have noticed that a poll panel just appeared. Your feedback is extremely useful to us, and we would greatly appreciate if you could take a couple of minutes to complete the survey. And then this concludes the presentation portion of the webinar. At this point, we will start the Q&A. All right, the first question that we have is someone asked, we already have controls models. Can I use them in this process?
Yeah, if you have controls models and you have the simulation model, you're able to use them in this process. It just depends how much of the controls model you're willing to incorporate. And this is definitely something our support is willing to help with. We can couple it to Simulink, or we could have GT Suite be the master and run the Simulink model. It just depends whatever you would want.
All right, thank you. All right, next question we have, are there any case studies that show this process implemented?
Yeah, our website has definitely a few publications on it, on the different phases, on developing the powertrain model for this, on incorporating it into your control system. And if you'd like to have us send you some, definitely don't hesitate to reach out to us, and we'll have a discussion and send you some material on this.
Great. Next question, how much testing can you really reduce?
So what we've seen with our customers is that it's just the iterative portion. Many of their processes require a physical test to finalize and proceed with the development of the program. So we're not saying to replace the test at all. We're wanting to enhance the test through the use of virtual calibration.
All right, great. Next question. Are there specific tests that you would suggest doing virtually?
Yeah, the low-hanging fruit that we see at a lot of customers is the controls validation section, the verification side. But definitely the robustness study is one that you should do in virtual. because because due to the tedious nature of determining whether your controls are robust. It's just large DOEs, large amount of testing, and this can all be done at the same time in parallel and virtual. I got another question saying to elaborate a little further on open loop virtual calibration in the absence of control system model in future webinars. Yeah, we can definitely elaborate on that. If you want to reach out to us, we can talk about that, or I can refer you to my blog. There's a blog about it. Basically, that would just be running large DOEs, getting an understanding of the operating space, using that to develop a baseline calibration. And yeah. So another question we got is, what kind of test will be required to confirm the robustness of the models? You would basically need to evaluate if your model is transparent to reality. And at that point, if it's predictive among a set of operating space that you have data for, a test data versus calibration data kind of thing, then you're able to confidently say, if you do a robustness study, that at least it's going to be valid directionally, if not absolute. I got another question where if one already has an engine model, could it be used with virtual calibration? Yeah, definitely. And it's better to use a physics-based model than a map-based model. The reason why is because the physics-based model actually can react. A map-based model is not predictive at all. It's just based off of your test data, and it wouldn't help for tasks like torque curve exploration because you don't have data for it. I think we got time for one more question. So what do you have to do to implement this process? Basically, we'll have a bit more information in the next webinar from a technical side, but I would say from the soft side, you would need buy-in on someone in the organization that has visibility to controls, calibration, and simulation group. And this would be key in order to drive this workflow.
All right. Thanks, Michael. And thanks to all of you for all of your questions. That's all the time that we have. If you missed a part of this presentation, or if you'd like to share it with a colleague, we'll soon be posting a recording to our website, and I will send you all an email once it's available. We hope you enjoyed today's discussion, and this concludes the webinar presentation.